Trigonometry, Chapter 7, Applications of Trigonometry, Vectors, Section 1, Oblique Triangles and the Law of Sines, Video 1, Congruency and Oblique Triangles. This series is based on content from Pearson's Trigonometry, 12th edition by Lial, Hornsby, Schneider, and Daniels. Up until now, when trigonometry has been used in triangles, they've always been right triangles with the right angle. But can we adapt trigonometric functions to accommodate non-right triangles, also known as oblique triangles? If so, how? Remember, in a triangle, our trig definitions are based on opposite, adjacent, and hypotenuse. But if we're not in a right triangle, then there is no hypotenuse. Now, the answer to the first question, can we apply the trig functions, is yes. But, excuse me. But before we answer the second question, how, let's briefly review the types of triangles and axioms that assure two triangles are congruent. Now, when it comes to classifying triangles, we can do it by the size of their largest angle. If the largest angle in a triangle is less than 90 degrees, in other words, acute, the triangle is called an acute triangle. If the largest angle in a triangle is exactly 90 degrees, a right angle, the triangle is called a right triangle. And if the largest angle in a triangle is greater than 90 degrees, obtuse, the triangle is called an obtuse triangle. So these descriptions, these types of triangles make perfect sense based on the size of their largest angle. Now, to determine when a given set of three measurements, a mixture of angles and or sides, determines a unique triangle, we refer to congruency axioms from geometry. One of which is side angle side, which says, if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the two triangles are congruent. For example, in triangle ABC and triangle XYZ, notice we have AC is congruent to XZ, indicated by the two marks on the segments. Angle ACB is congruent to angle XZY, indicated by the triple arcs on both angles. And side CB is congruent to side ZY, indicated by the single marks on both sides. This is an example of side angle side. We can trace out a side, two sides, and the angle between them. Side, angle, side. If you have a side angle side set on one triangle that is congruent to a side angle side set on another triangle, then the two triangles are congruent, which basically means the remaining sides and angles are also the same. Angle side angle is another congruency axiom in geometry. If two angles and the included side of one triangle, such as angle CAB, side AB, and angle ABC, are congruent to two angles and the included side of another triangle, then the two triangles are congruent. Again, we can see that here that we're looking at angle side angle, because if we started in an angle, trace out the side included and go to the other angle, we've gone angle side angle. And we can tell by the marks here that angle CAB is congruent to angle ZXY, the single arced angles. Side AB is congruent to side XY, indicated by the three marks on the sides. And angle ABC is congruent to angle XYZ, indicated by the two arcs in each angle. Since we have an angle side angle set on each triangle that are congruent, then the two triangles are congruent by the angle side angle congruency axiom. It's actually a theorem, I believe. We can also draw the same conclusion with side, 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 which basically says if all three sides of one triangle are congruent to three sides of another triangle, then the two triangles are congruent. In other words, if all the sides are the same, then all the angles are the same. As a consequence, when given the following information about a triangle, a unique triangle should exist. The measures of two sides and the included angle, the measures of two angles and the included side, or the measures of three sides. This is provided the sides satisfy the triangle inequality, which basically says any two sides have a sum greater than the third side. It's also worth mentioning that the measures of two angles and a non-included side, angle, angle, side, if you will, determine a unique triangle, since knowing the measures of two angles determines the third angle, so we know the side and the two angles on either side of it. In other words, ASA, angle, side, angle. Lastly, let's address the situation where a triangle is not uniquely determined, given the measures of two sides and a non-included side, sometimes called SSA. I guess you could say it the other order, but you can tell why we don't. In such a case, it's possible there could be 0, 1, or 2 triangles. We will learn what criteria leads to each of these possibilities. Specifically, if we know that two sides are congruent and an angle not between them is congruent, we cannot conclude anything without more information. There is no now you try for this video.